Sure, I'm ready.
Okay. Hello, everyone. Good morning, afternoon, evening, and welcome to the second day of our MTV Nuclear Engineering Summer School. My name is Sean Clark. I'm the MTV Associate Director, and I'll be moderating today's lecture. As a reminder, for questions, please use the Q&A feature in the webinar. Type those in during the lecture, and we'll take those at the end of the presentation. So today I'm happy to introduce Dr. Richard Kouzes, who's a laboratory fellow at the Pacific Northwest National Lab, which is a Department of Energy laboratory on the west coast of the United States. He's working there with research in the areas of neutrino physics, as well as homeland security and detection technology. So today he's going to give us a lecture titled Radiation Detection and Applications, and we look forward to hearing from him. So Dick, the floor is yours.
Thank you, Sean, for the introduction. It's a pleasure to be here virtually. Today, I'm going to talk about radiation detection and its applications. I was asked to give some introductions, so I'll start off with that. If I can make this advance. Okay, for some reason, there it is. As Sean mentioned, I'm from Pacific Northwest National Laboratory, which is one of the Department of Energy national laboratories located in Eastern Washington. Currently, I'm down here in Reno, Nevada, speaking to you. You see that there are quite a number of national labs run by the Department of Energy across the U.S. PNNL is about 5,000 people and about $1 billion a year, spanning pretty much every area of science and engineering. Today, I'm going to talk about some radiation detection basics, and then I'm going to talk about a number of applications. These four in a little bit more detail, dealing with border security, safeguards, neutrino physics, and muon tomography. So let me start off with some basics. First, I want to remind you of the energy scale. I'm going to be using units of electron volts. An electron volt is the energy associated with visible light and atomic or chemistry. It's equal to 1.6 times 10 to the -19 joules. On that scale, X-rays, which are due to transitions of the inner electrons of atoms, have energies on the order of kilovolts, thousands of electron volts. And nuclear decays that we're going to be talking about have energy scales in the millions of electron volt scale. So just keep that in mind. So when we talk about radioactivity, we often mean alpha, beta, and gamma decay. So just to remind you, alpha decay is when a heavy nucleus spits out a helium nucleus, 2 protons and 2 neutrons. Gamma decay is due to transitions within the nucleus of protons and neutrons. They're excited and then decay back to a stable state and emit gamma rays, which are energetic photons. The other form of decay, beta decay, can be either beta minus or beta plus decay. In beta minus decay, a free neutron or a neutron inside a nucleus can transition to a proton plus an electron and an anti-neutrino. So this is a weak interaction process. Positive beta decay is when a proton inside of a nucleus can transition to a neutron plus a positron and a neutrino. And let me just remind you that X-rays, which are also often present, come from atomic transitions of the electrons in the electron shells of the atom. There's also fission, which is an important process that occurs in very heavy nuclei. It can be either spontaneous or induced. So spontaneous means the nucleus just decides to fission. Induced means that a neutron, for example, comes in, excites the nucleus, and then it fissions. In fission, you get 2 heavy products plus 1 to many neutrons coming out of various energies. Plus you get gamma rays because these excited fission products will be emitting gamma rays until they reach some stable state. On the bottom right here is a plot of the energy spectrum associated with the neutrons that come out of fission. The dark line here is the spectrum that is common to all fissions, whether induced or spontaneous. This happens to be a californium spectrum, but a plutonium neutron spectrum looks very, very similar to this. The other curves shown here are other neutron sources, which are typically forms like ambium, americium, beryllium, where the americium alpha particle excites the beryllium and causes a neutron emission. So you can get neutrons of various energies. Fission gives you energies all the way up to around 10 MeV and all the way down to low energies. And these other neutron sources can be up to slightly higher energies and of course, spanning the entire range of energies. Now, when you have materials like uranium, it undergoes spontaneous fission, as I mentioned, and it has a half-life of about 4.5 billion years, so comparable to the age of the Earth. So about half of the uranium that was in the Earth when it was formed has decayed by now, and that provides the heat in the core of the Earth. Uranium alpha decays down to thorium-234, which lives about 24 days, which beta decays to palladium-234, which beta decays to uranium-234, and so forth. All of these decays, of course, emit these alpha and beta particles and gamma rays in the process. And this is part of what constitutes the gamma ray background that we observe in nature. This decay process of U-238 ends up producing radon, radon-222, which has a half-life of 3.8 days, and is the radon that's of concern in homes because this lives long enough to percolate out of the soil and get into your house, and yet it's short enough that it can stay in your house and decay. And if you breathe it, it can cause damage to the lungs. Eventually, uranium-238 decays down to lead, and that's its stable end product. If we think about backgrounds, backgrounds are important not only to our health, but also to radiation detection. Backgrounds are always present, and whenever we do detection, we have to worry about the background that's present, that we have to see a signal above. So the backgrounds come from uranium, thorium, potassium in the soil, from radioactivity that's in foods, from cosmic rays. We get bombarded continuously with neutrons, muons, and neutrinos coming from cosmic rays. These are energetic protons and some helium nuclei in the upper atmosphere, producing pions, which decay to muons and produce neutrons as well. So we are currently being bombarded with a little over between 100 and 200 neutrons and 100 to 200 muons per second continuously because we live roughly at sea level. Meanwhile, we're getting hit by about 1 million neutrinos per second through our thumbnail in size. So we get hit by a lot of those, but of course, those are weakly interacting particles. They're not charged, and so they do a lot less damage than these other particles. In addition, we're exposed to radon coming out of the soil, as I mentioned in that decay, and medical exposures. Here in the US, our medical exposure is actually our dominant radiation that we receive. So let me briefly mention photon interactions with matter. So photons, gamma rays and X-rays, can interact with matter in 3 different ways. For lower energy, the photoelectric effect is important. This is where a photon hits some material and an electron is emitted in the process. This process, the description of this process is what Albert Einstein got the Nobel Prize for in 1905, from his 1905 paper, rather. The second process is the Compton effect, which is important in intermediate energies. In fact, most of the interactions we're going to be talking about will be from the Compton effect. The Compton effect is where a photon comes in and scatters off of an electron, giving energy to that electron, and the photon continues on its way at a reduced energy. That is, as I said, the most important product of intermediate energy photons. And for higher energy photons above about 2 MeV, you can get the pair production process. This is where a photon passing near a nucleus can convert directly into an electron and a positron pair. So this is a good example of Einstein's E equals mc squared, which is another one of the papers he wrote in 1905, but was not what he got the Nobel Prize for. So these 3 processes all cause the loss of energy by photons in matter by producing energetic electrons and positrons. These electrons and positrons then lose energy by producing more electrons and ions within the material. And so the net result of photon interaction in matter is energetic electrons and ions are produced. Now let's look at charged particles like protons or muons or energetic electrons in matter and alphas. Alphas, betas, and protons and so forth all interact by scattering off of electrons in material, losing energy through multiple scatters, and again, producing energetic electrons and ions in the material. The energy loss by these charged particles in matter is represented by this curve here, which typically shows a Bragg peak. That is, they lose energy slowly and then they reach a range where they tend to lose most of their energy at one distance. Neutrons are not charged, and so they interact through the strong process by hitting a nucleus and elastically scattering or being absorbed by a nucleus. In the process, again, they end up emitting energetic particles, protons, for example, energetic protons, or photons from absorption. And in the end, the result again is a bunch of energetic electrons and ions are produced in this process. So in general, what we've seen is basically the interaction of everything in matter is the production of energetic electrons and ions in the material. Now, when we talk about the ability to detect radiation, we have to consider a number of parameters. So the first thing is, what is the activity of some source of radiation we're looking at? And how long do we have to make a measurement of that source? There's then a geometric effect. That is, how far away are we from that source, between the source and the detector? And there's a 1/r² dependence in that measurement capability. Once a particle hits a detector, we have to consider what's called its intrinsic efficiency. That is the efficiency of detection. If a particle hits a detector, what's the probability that it will produce a detectable signal? Our detectability then depends upon shielding. If we put shielding between the source and the detector, that's going to reduce our ability to detect that source. And then there's background. As I mentioned, we have to have the statistics in our signal to see the signal above whatever background is present. So that's an important parameter. And finally, there's either an automated or an expert analysis that has to take place to say what this source is or the fact that we have detected something. So we're going to be talking about detector types, and detector types could be made of gases, liquids, or solids. So first, let's consider gas counters. Consider a cylinder filled with some gas, and running down the middle of the cylinder, we typically have a wire, a thin wire, with some voltage on it, typically a positive voltage. If an alpha, beta, or gamma comes in and hits the gas, it will lose energy and generate a bunch of electrons and ions. Or if a neutron comes in and hits a helium nucleus, for example, it'll be absorbed, generating a proton and a triton, and those end up resulting in, again, a number of electrons and ions that are freed. If we put a positive voltage on this wire, the electrons will drift towards the wire, and in a few microseconds, they will get next to the wire. If the voltage is fairly low, the signal will not be amplified, and we call that an ionization chamber. If the voltage is higher, the electrons, when they get within one wire radius, will avalanche and produce additional electrons that then are collected by the wire. And if the voltage is right, the amount of signal we get out of this wire will be proportional to the number of electrons produced in the first place. That is the energy loss of whatever it was that hit this detector. And we call that a proportional counter. If we crank up the voltage even more, so that for any number of electrons produced, we get a large signal, we refer to that as a Geiger counter. Now, the second type of detectors that we will refer to are scintillators. These can be typically liquids or solids. although gases can also be used as scintillators. In this case, a particle like an alpha, beta, or gamma comes in, interacts with the scintillator, generates ions and electrons. These then, through atomic processes, will either go through relaxation of molecules or absorption of these electrons, producing excited atoms and molecules, which then emit photons, visible photons typically. These visible photons bounce around within the scintillator and eventually can be collected by a photomultiplier tube or some other photo detector like a silicon photomultiplier. And that generates the signal that we see. As I mentioned, these can be liquids. Liquids are often used for neutron detection, for example, and solids can be organic or inorganic. And I will talk about examples of those. Another form of solid detector are semiconductor detectors. These are not scintillators. Instead, these are materials that can be back biased, which means that you put a voltage on them, but there's no current that flows because they are semiconductors. And so there's a strong electric field produced within this material. So you can think of this object as a large capacitor. So there's charges on the anode and cathode. And when a particle interacts inside of this solid, it generates, again, electrons and holes. The voltage causes the electrons and holes to drift toward the anode and cathode within this solid. There is no amplification that occurs. So if the noise is low enough in this material, we can collect those electrons and holes and we get a signal out of this device. These are typically made out of germanium or silicon, although there are newer materials like cadmium zinc telluride that are semiconductors. But germanium has to be cooled to liquid nitrogen temperatures in order to keep the noise levels down. On the other hand, silicon can be used near or at room temperature and has been used for years for radiation detection. But germanium at cold temperatures like liquid nitrogen gives us the very best signals that we can observe, the best resolution, down to levels about 0.1% in energy resolution. Some of the new materials like cad zinc telluride can approach that level, but not quite as good as germanium. So for gamma ray detection, we can look at some different detectors. We talked about gas counters. They can be ionization chambers, proportional counters, or Geiger counters. They typically don't have great resolution, but they allow us to detect a signal. Scintillators can be organic or inorganic. An inorganic scintillator, for example, is sodium iodide. It's typically used in like handheld detectors shown here. There's others like cesium iodide shown here that might be used on a pager. They can be larger, but when we think about large scintillators, we tend to think about things like plastics, polyvinyl toluene being the most common, polystyrene being another example. These large plastic scintillators can be made relatively cheaply. They can be made very large. They don't have anywhere near the same energy resolution as sodium iodide. That's because in sodium iodide, you get the photoelectric effect and the Compton effect and possibly pair production, but you get total absorption of the gamma ray. In plastics, you typically only get Compton scattering. So you don't see the full energy peak because the density of plastic and the atomic number of plastic is so low that you only get the Compton scattering. So shown here in the upper picture is an example of a large detector that has plastic scintillator in it. It's large, it's inexpensive, it's robust in the environment, and therefore it's used for these large types of detectors, whereas sodium iodide might be used in smaller detectors like these handhelds. High purity germanium, I mentioned, has to be cooled to liquid nitrogen temperatures, so they typically have a form factor with a large dewar, and they are, tend to not be very large. Maybe a kilogram is a large sodium high purity germanium detector. Alpha and beta detectors might be scintillators or gas counters. They are used usually for survey purposes and not for spectroscopy as much as gamma rays are. For neutron detectors, even though neutrons are emitted with high energies, we typically detect them by moderating them with plastics. If you put a plastic like a polystyrene or polyethylene around a detector, you can cause the neutrons to scatter off the protons and thermalize themselves, reach room temperature, and therefore they can then be captured onto helium-3, which is the most common neutron detector. There are detectors for fast neutrons, such as liquid scintillators, and some plastic materials. But like I said, these thermal neutron detectors are much more common. Shown here is a large neutron detector, again, on the scale of a radiation portal monitor type application, surrounded by a moderator material and a helium-3 tube inside. Neutrons are emitted from special nuclear material like plutonium and uranium, and also from sources like californium. So neutrons are of particular interest for when I talk about border security. And the other reasons they're of interest is that the background that's present for neutrons is only from cosmic rays, typically, and it's about a 1,000th of the background rate of gamma rays. So it's easier to see a small neutron signal than it is to see a small gamma ray signal in terms of intensity. Thermal neutrons behave like a gas. They bounce around and therefore are more difficult to shield than gamma rays are. So let me talk about some applications now. I'm going to talk briefly about a few application areas, and then I'm going to talk in more detail about some of these specific applications. So the first application I want to mention is medical. Radiation detection is used extensively in medical diagnostics, X-rays, for example, computed-aided tomography, positron emission tomography, single photon tomography, for example. All of these require radiation detection, and usually those detectors are scintillators, very commonly used in those. Of course, X-rays were initially detected 130 years ago on film, the discovery of X-rays. In addition, there are radiopharmaceuticals that are delivered into the bloodstream, like technetium-99m, which is used widely in stress tests. So in fact, Tech-99m is the most common radiation burden that is carried by people in the US. About 1 in 2,600 Americans carries a Tech-99m burden at any given time. In addition to medical diagnostics, you also see radiation detection used in therapy, when therapy is being delivered either by injected pharmaceuticals or inserted radiation sources, or by electron beams or X-ray machines. There, of course, are detectors present to measure the dose delivered to the patient. Second type of application I'll mention briefly are industrial radiators and radiography. We see here a typical source that might be used for radiography or irradiation. These are the sources shown on the bottom left here that are typically shielded inside a handheld device like this. There are, on the upper right here, this shows a large facility for industrial radiators, where a very large source, many Curie's sources, are used for sterilization. Sterilization may be used for food products, or it may be used for things like medical instruments and so forth. So irradiation of materials is pretty widely done in the US. For radiography, I show here a picture on the bottom right. This is a picture I took at a shipyard down in Texas. In the shipyard, they roll steel into cylinders and then weld it along the edge. And in order to guarantee the soundness of the weld, they place a radiation source. You see here in the bottom, that's the little source at the end of this little tube. That tube can be pulled back into the shield here. The source is put out. It's a very hot iridium-191 source. And film is placed along the weld up here on the top, and the film is exposed to the radiation and then developed to see the quality of the weld. So that's done particularly at shipyards around the US, but it's widely used to image welding. The next type of application is for oil and gas exploration. There's a process called well logging where radiation sources are placed down into wells that are being drilled to look for the presence of gas and oil. So in this type of example, there's a neutron source and some helium-3 neutron detectors that are put into this collar that's slipped down into a well that's being drilled. And if there's protons present from oil and gas or from water, you will get a reflection of those neutrons back into the detector, and you can determine where the oil and gas is in this well. So there are hundreds or thousands of these types of sources that are scattered around with the associated detectors. Another industrial application is for construction. Shown here on the bottom is what's called a Troxler gauge. It's a small device that has both a gamma ray source and a neutron source, and gamma ray detectors and neutron detectors. And it's used for measuring two properties. One is the density of the material that it's measuring, and the other one is the water content. So this is used for measuring the dryness of concrete or the dryness of soil and the density of the material. So again, these are actually carried around in pickup trucks around the country at construction sites. Another application is for neutron scattering science. This is used for both basic science and for applications. An example is the spallation neutron source, which is located at Oak Ridge National Lab in Tennessee. They have over 120,000 liters of helium-3 used at that facility. They have a number of detection systems. I show here in this picture a detection system that's actually at the ILL in France. Each of these vertical objects are helium-3 tubes that form an arc around a target position. Thermal neutrons or epithermal neutrons are scattered off of this target and are detected in these helium-3 tubes. So it measures a diffraction pattern, basically. And this is used widely for structural biology and chemistry and material properties. There are a number of neutron spallation sources around the world, the NSS being the major one in the US. So now let me turn to 4 topics more in depth. The first of these topics I'm going to talk about is border security. For border security, we want to be able to detect weapons of mass destruction or the materials to build weapons of mass destruction crossing the border into the United States. We also are interested in radiation dispersal device materials that could be brought into the country. So we have placed detectors, large detectors shown here, which are called radiation portal monitors. Each of these detectors contains a large gamma ray detector made out of plastic and helium-3 tubes for neutron detection. Under a program that PNNL ran, we placed radiation detectors at every US border crossing. These include land border crossings with Canada and Mexico, seaports on the West Coast, the Gulf Coast, and the East Coast of the US, as well as Alaska, and airports scattered throughout the US. The quantity of material that passes through these borders every day is massive, many, thousands of trucks, thousands of people, and thousands of containers, particularly brought in on ships. And the goal is to screen 100% of all cargo and people and vehicles entering the United States. In this program, which PNNL has run for the last 22 years now, we decided on the use of radiation portal monitors for this purpose. Radiation portal monitors, as shown here and in the previous picture, again, they contain large gamma ray detectors and large neutron detectors to look for weapons of mass destruction, or any radioactive material that's present. These are highly efficient gamma ray detectors and neutron detectors, and they provide rapid screening of vehicles coming across the border. Here's some other examples of such portal monitors deployed. Here's an airport where cargo containers are screened before they go on airplanes. Here's a package facility where packages on a belt are screened by these portal monitors shown above the belt. We built some mobile portals that can be used for temporary deployments. And shown here are permanent deployments, this being San Ysidro coming into California, where there are over 30 lanes of portal monitors present for all these vehicles crossing into the US. In addition to those radiation detectors, there's often imaging produced at the border as well. Trucks are scanned with large X-ray imaging systems to look for contraband cargo. An example is shown here. These are humans being transported across into the US from Mexico in one of these images. And down here on the bottom are some suspicious items shown inside of a tank of liquid coming across the border. So that's border security. Now I'm going to talk about nuclear safeguards. Nuclear safeguards is the purview of the International Atomic Energy Agency, and a number of us have worked with the IAEA. The purpose of the IAEA is to ensure that declared nuclear material remains under a nation's control and complies with international agreements. And to do that, the IAEA sends inspectors out to look at enrichment plants for enriching uranium, fuel fabrication plants. They go to power reactors, fuel storage facilities, and spent fuel reprocessing plants. To do their work, they use a variety of methods. They use tags and seals, but in radiation detection, they use gamma ray detectors to determine the isotopics, for example, of uranium or plutonium in fuel. They have a declared value of enrichment in the fuel, and they can do gamma ray detection to verify that enrichment. So high purity germanium detectors are very often used for this purpose. And you get these spectra out of high purity germanium, which are sharp lines representing the nuclear transitions in that particular nucleus. The other type of detectors that the IAEA uses are neutron detectors. These are, again, typically helium-3 based neutron detectors that are used in this example. We have a fork detector, which is inserted into a cooling pond to look at spent nuclear fuel. So here you see a fork detector measuring a spent fuel assembly in a cooling pool at a facility. And the idea here is to see that the gross neutron counts are consistent with the declared age of this fuel. A second type of detector that is used by the IAEA are uranium neutron coincidence collars. These are used to measure the properties of fresh nuclear fuel, be it uranium-based fuel or MOX fuel that might contain plutonium. This is a detector with many neutron tubes, helium-3 tubes typically, wrapped around the fuel in this assembly. And there's a moderator, the white materials moderator. For plutonium fuel, which emits neutrons spontaneously, this is used in what's called passive mode. So it's simply measuring the neutrons emitted from the plutonium spontaneously emitted. The detector measures the gross number of neutrons, which is referred to as singles, and it also measures the coincident neutrons within a given time period, which is referred to as doubles. So this measures singles and doubles. And from that, the detector can determine in about 15 minutes to 1% accuracy that the fuel assembly contains the material as declared. For uranium fuel, since uranium emits fewer neutrons by about a factor of 10,000 or so, This is used in ActiveVode. In that case, a lithium and an americium lithium source is very often used inserted into this holder here. And so neutrons are impinged upon the assembly, inducing fission. And those induced fission neutrons are then measured by the detector. And again, the idea is to see that the fuel meets the specification declared by the owner of the fuel. So that's what I'm going to say about safeguards. We'll come back a little bit to safeguards later, but let me now talk about neutrino science. You may be familiar with the fact that neutrino detection has been discussed recently for possible use in safeguards. And I will refer to that a little bit, but mostly I'm going to talk about the science, where this all came from. So the neutrino was postulated by Wolfgang Pauli in 1930, and the reason was to conserve energy and momentum in beta decay. And he made an interesting statement in 1930. He said, "I have done a terrible thing. I've postulated a particle that cannot be detected." And then the neutrino was detected in 1956. So it took 26 years, but it was eventually detected and that was done by Fred Reines. So if we look at neutrino experiments or neutrino applications, the first of these that's important are solar neutrinos, which I'm going to talk about. Then there are neutrino mass measurements, neutrino oscillation experiments, neutrinos double beta decay. And then I mentioned reactor monitoring for safeguards as a possible use of this technology. So it was in 1938 that Hans Bethe described how the sun might produce energy by fusion. Up until this point, we did not know how the sun created its energy. Gravity can't explain it. Burning can't explain it. But so in 1938, Hans Bethe described this process, and he got the Nobel Prize for that. In the fusion process in the sun, we start off with protons, hydrogen, and two protons fuse together in a weak interaction process, producing deuterium, a positron, and a neutrino. So this is the major source of neutrinos from the sun. The process in the sun continues because the deuterium fuses with proton to give helium-3, and then it goes on and you get two helium-3 fusing, give helium-4 and two protons, and so forth. So there are other sub-reactions. The net product is that 4 protons end up producing 1 helium-3 nucleus. And that is what powers our sun, we know now. And at the time, Bethe postulated this. So in the late 1950s, Ray Davis, who was a physicist actually a chemist at Brookhaven National Lab at the time, decided to build an experiment to make a measurement to show that, in fact, neutrinos were produced and that the sun did generate energy by fusion. He put 100,000 gallons of dry cleaning fluid into a very large tank, shown here in this picture, deep underground in a gold mine in South Dakota. He was looking for the inverse beta decay reaction. An electron neutrino from the sun would hit a chlorine nucleus in this dry cleaning fluid, producing an argon-37 nucleus and an electron. So this is referred to as inverse beta decay. The argon-37 has a 35-day half-life. So every 2 weeks, Ray would bubble helium through this tank of dry cleaning fluid and collect the atoms, and he'd separate out cryogenically the argon. He'd mix in some natural argon and put these into very small proportional counters. So this is a very small glass tube with a metal lining and a wire down the middle. And he put the sample into this very small tube, which is smaller than your little finger. And he would then count it, looking for the decays of argon-37. Now, in a month, you would only expect 2 or 3 atoms to be produced by solar neutrinos. So he's looking for a very, very small signal. So he did this for many, many years. And at the end of that time, what he found was that the theory of the sun, shown here in bars on this plot on the left, gave a prediction as to what Ray would see in his experiment. These predictions were done by a physicist named John Bacall, who was at the Institute for Advanced Studies, shown here on the right. But Ray's measurement, shown in the white bar here, turned out to be 1/3 of the number of counts that he expected to see. And that lasted, as you see here, 30 years. He made measurements, and his value never changed. It was always about 1/3 of the expected rate. So back in the 1970s, when I actually got involved with this work, there were three possibilities. We knew that Ray had a measurement. So either the solar model that John Bacall developed was wrong, or Ray's experiment was wrong in some way, or very unlikely, maybe there was new physics that was occurring. And then Ray got the Nobel Prize for this work in 2002. Jump forward to 2001. There were a number of other experiments done, but sort of the clincher on this problem was what's called the Sudbury Neutrino Observatory Experiment, SNO, which ended up winning the Nobel Prize in 2015. SNO consisted of 100 tons of heavy water placed into an acrylic vessel. This is a very large vessel, as you might imagine. And that was surrounded by phototubes, as you see here on the right. All of those little things there are phototubes that are looking for the scintillation and Cherenkov light generated within this heavy water. And that is then surrounded by natural water as a radiation shield. This again is deep underground, more than a mile underground. So after a number of years of running of this experiment, the experiment produced a result. Now, the thing that was new about SNO and unique, and which helped solve this solar neutrino problem, was the fact that it observed three different reactions. Electron neutrinos from the sun could cause inverse beta decay on deuterium, producing 2 protons and an electron. And it could also observe the induced fissioning of deuterium into a proton and a neutron through the weak interaction process. This is just simply breakup of that nucleus. But this could be induced by any neutrino. It didn't have to be an electron neutrino. So by this point, we knew there were electron neutrinos, there were muon neutrinos, and then there were tau neutrinos. So there are 3 neutrino flavors that existed. And this detector could measure all 3 of those. And in addition, there was an electron scattering process. A neutrino of any flavor could scatter off an electron, giving it energy, and that signal could be observed. So this detector could observe all 3 signals. So when we released our results from SNO, what we observed was that we verified Ray Davis's claim, that is, electron neutrinos from the sun generated a signal shown here in red that was 1/3 of that predicted by the standard solar model. The hash here is the standard solar model prediction. So the electron neutrinos only produce 1/3 of the signal. But when you go to the signal produced by all neutrinos, you find that it agrees perfectly with the standard solar model. So this verified that all neutrinos produce the correct signal. And this meant that there must be neutrino oscillations. That is, the neutrinos produced in the sun as electron neutrinos, by the time they reached Earth, they had converted 1/3 to electron neutrinos, 1/3 to muon neutrinos, and 1/3 to tau neutrinos, roughly. And this meant the neutrino must have mass. So that postulate back in the 1970s that there might be new physics actually turned out to be the answer to the solar neutrino problem. So that's what I'm going to say about solar neutrino, or about neutrinos. Now I'm going to turn to the application for muon detection. Muons are used for a wide variety of detection applications. The main detection for muons is actually to delete them or eliminate them as a background in other experiments. So muons are a background for neutrino detection experiments, for dark matter experiments, and for neutrinos double beta decay experiments, for example. So muons are detected in order to veto them out of the signal. There, of course, are muon experiments done at like LHC and Fermilab to directly measure the properties of muons. But what I'm going to talk more about is tomography. Muons that are produced in the upper atmosphere come down toward the Earth, and they come mostly vertically. It's a cosine squared distribution with angle. And they've been used to image volcanoes. They've been used to image pyramids. They've been proposed for tunnel detection. They've been proposed for use in carbon CO2 storage, underground storage, which I'll say something about. They've been used to look at possible of using them for spent fuel storage container applications. And they've been tested for viewing images, viewing vehicles for Homeland Security border crossing applications. The reason for that one is that muons are scattered most highly by high Z materials. And so it's easy to detect special movement materials in the presence of other materials. Shown here is a picture from Decision Sciences of a large muon detector system that you could actually drive a truck through that they built. So just to show you how you detect muons, it's very easy. Shown here is on the top black object here is a large polyvinyl toluene gamma ray detector. And the bottom, same thing. And they're simply spaced apart by some distance. And so I measured the muons coming through both of these panels. At sea level, there are about 160 muons per square meter per second coming in. So each of these panels, got roughly 200 muons per second hitting them. On the right here is shown the spectrum measured from these panels. The white line or the lighter line here shows the single signal, the signal that just came from both panels without coincidence. And the red signature here is the coincidence between these two panels. So you can see that by providing coincidence between the signal observed in both these panels, you get a rejection of most of the background that's present. By the way, this peak here in this case is around 10 MeV in equivalent energy compared to around 1 MeV for the gamma ray background. So if you have two detector panels like those shown that could measure position in X and Y, you can measure X and Y in two planes and therefore get the direction of the muon and the intensity in that direction by making measurements over time. Shown here in the bottom right is an example of such a detector. It has crossed fiber optic wires and can measure the XY position in this plane of PVT. So by measuring the incoming energy or incoming angle and intensity as a function of direction, you can perform tomography on objects. You can do that by placing a material between the two detector sections, or you can put the detector below an object you want to measure. This is what was done in the Khufu pyramid by a team from France, Japan, and Italy. You may have seen recently the results from that. They discovered some unknown rooms in the large pyramid. The intent of this detector I'm showing here was that we are planning to measure the Khafre pyramid, the second pyramid. And for that experiment, we're going to place that detector into the center bottom of the pyramid. It's where the sarcophagus room is, and look for the angular distribution of muons coming through the pyramid as a function of angle. And this will be a many-month measurement because the rate of muons is very low, and particularly since it takes about 50 GeV muons to penetrate through the pyramid. So you're only looking at muons above about 50 GeV. Muons of lower energy, where the bulk of the spectrum is, cannot penetrate this far. The detector we designed was very specific because it had to be less than about 1 meter in size because we had to carry it through these small tunnels. So it has to be hand transportable, and it couldn't contain any toxic or asphyxiating gases. The gas counters that are used for many muon detectors would not be allowed because they contain asphyxiating gases. So anyway, that's the application of muons. Another application of muons, this is a picture from Los Alamos. Los Alamos placed large muon detectors on either side of a concrete spent fuel storage container at Idaho National Lab. This uses gas proportional counters to measure muon passages. The muons are measured actually 3 times on each side. So you again can determine the trajectory of the muons and how they're scattered inside this material. And from that, you can form an image of the spent fuel that's present inside of that container. One of the groups involved with the MTV are working on this muon scattering experiment. So anyway, that's another application of muons. Yet another application that's being done by Los Alamos is to image the interior of the Duomo on the Florence Cathedral. They have gas counters. Again, here, the gas counters shown here for this assembly. They're placing gas counters on the inside of the dome and the outside of the dome to try and image the material that's in between the stone layers of the inner and outer dome construction, because they don't know what the actual construction is in between the stone material. Another application that we worked on was for carbon sequestration, which may seem a little odd, but the idea is if you bore a hole, drill a hole underneath a carbon sequestration site shown here, you can measure the muons penetrating through that carbon sequestration site. As you inject CO2 into this site, you displace brine, and the CO2 actually turns into a superfluid, and the density changes. So you can measure the density change in the sequestration site by doing muon measurements over time. And the idea is to watch the CO2 being put into place and then watch that it stays in place over time, that it doesn't leak out. We developed a prototype for this, but it was never funded for deployment. So that's the end of my discussion of applications. I wanted to say that radiation detection is a very important and wide-ranging field. I have not discussed computer applications, which I should say something about. Computer simulations with MCMP and GEONT and others are exceedingly important to all of these experiments. When you design a radiation detector, you usually simulate it to determine what you would expect for a signal. For the case of muon detection, for example, the only way you can reconstruct the information is by computer simulations and comparing the simulations to the detected signal. So computer simulation is an exceedingly important area for radiation detection. As you've seen, the gamma ray, neutron, neutrino, muon detection is a very active field involving many types of physicists, chemists, engineers in the development of these technologies. And so there are lots of opportunities for future development of these technologies. I'd like to acknowledge that this work has been supported by the U.S. Department of Energy, U.S. Department of Defense, U.S. Department of Homeland Security, and by PNNL and other laboratories. And with that, I'd be happy to take any questions you might have.
Thanks, Dick. Very nice presentation. We have a number of questions in the chat. We have about 10 minutes left, I think, in our time. So I will get through as many as we can, and I'll group some together. There is some overlap here. So the first question is related to the last point you made about simulations. Can you talk about any Monte Carlo techniques that are available to simulate UV photons, visible photons?
Visible?
Yeah, UV or visible.
Oh. Well, I think actually Sarah can probably answer this better than I. I mean, there is capability within GEONT and MCMP for some visible photon simulations. For example, transport of these photons within a scintillator, for example. But I'm not the expert on that. I think Sarah is more of an expert there.
Yeah, I can chime in as well. You're right on track there. And GEONT4, being open source and flexible, the user can kind of do whatever they want as long as there's data. MCP is a little bit newer capability. So I think the challenge there is in the data. I see Sarah's typing something in the chat there too. So Cool. The next question, and there's a couple questions actually about medical sources. So you were talking a lot about background radiation, sources of background, and you were lumping in medical isotopes as a source of background. So can you, the question is, why are they considered background when they're kind of man-made, so to speak? So can you talk a little bit about why medical sources are commonly considered as background?
Well, there are two aspects there. One is that for health effects, every time we're exposed to medical treatments or diagnostics, that affects, potentially affects your health. In terms of probably more importantly, Homeland Security, since I mentioned 1 in 2,600 Americans carries a radiation burden, that means when we have, on the southern border sites, 50,000 people a day passing through that site, there are many, many radiation alarms produced by people. And those have to be separated from, items of concern. So in that sense, it's a background within that environment for that application.
Great. Clarification on pair production. So the rest mass, is 1022 keV, but we talk about pair production being relevant above kind of 2 MeV. So can you just clarify pair production a little bit?
Sure. I mean, there's a threshold. You get 2 511 gamma rays, and excuse me. You convert the photon into two electrons, each of mass 511 keV. So you have to be above 1 point something MeV. But if you look at you have to just look at the data that says how does the photon convert? And it just turns out that it becomes much more important above about 2 MeV. It is present below 2 MeV, but it just requires, it just isn't the dominant effect.
Cool. Let's see, helium-3 tubes. So helium-3 tubes, they're often existing in tubes, right? So this person is asking, wouldn't a plate-like geometry be better, more efficient in terms of surface area for detectors? So why do we always see helium-3 in like a cylindrical geometry?
So I think the main reason, it's convenience, but what has to be present in when you make a sealed detector, a sealed gas detector, you have to worry a lot about contamination. These detectors, helium-3 detectors, live for dozens of years, and they operate without problems. And the reason is they're produced in very clean environments with very clean materials. If you get, oxygen or water, for example, inside of a proportional counter, it will very quickly poison the detector. It'll cause the electrons to be absorbed before they can reach the wire, and therefore it kills the tube. So when you make a square detector or a different geometry, it's more difficult to control the materials you're using for that process. If you have a round detector, you get a uniform collection, you have a uniform electric field, the ions and electrons drift in a uniform way. If you have a flat detector, you have to put in multiple wires in order to accomplish the same thing. One of the things you have to worry about on a proportional counter is the wire tension. The wire has to be tight in order so it doesn't bow under the electric field, for example, or it doesn't vibrate, because those introduce noise into the system because the capacitance changes. So simply the round geometry is much easier to produce and control for production.
Okay, speaking about noise in detectors, there's a question about noise contributions in solid state detectors. So specifically, they're asking, what do you feel is the biggest noise contributor in solid state detectors?
So if we're talking about semiconductor detectors, it's the band gap that determines whether the material has to be cooled or not. So the band gap on germanium is pretty small. So at room temperature, you get a lot of thermal excitation across the band gap, and that produces noise. So you have to cool the material. But these are very high purity materials, but there's still contaminants present. And those also contribute to sources of crossing, shortening the band gap and causing thermal noise. Silicon has a slightly larger band gap and therefore is less sensitive to noise, but It does not have the same resolution for the same reason, because the band gap is larger. As you go to larger and larger band gaps, you become less sensitive. So gallium arsenide has a larger band gap, which allows it to operate at elevated temperatures, but its resolution is not as good. So that is basically the reason.
Okay, we're right at 2 p.m. here, but there's a couple more I want to take if you have time. Is that okay?
Sure.
Okay. What about the importance of detecting neutrons from cosmic radiation in terms of applications? How important are cosmic neutrons?
Well, so cosmic neutrons are the main background you have for detectors that are sitting, on the surface of the Earth. The rate is relatively low. So it is an example, a 6-foot helium-3 tube in a moderator might have a background rate from cosmic neutrons of, 4 or 5 or 6 neutrons per second. So it's relatively small. That allows you to detect a similar size source of a few neutrons per second. But it is the limiting factor for that detection purpose. It's less important for, where you have large neutron sources you're trying to detect, or you're measuring scattering. So it definitely depends on the application. For surface-based detectors, if you're trying to do muon detection, if you're trying to do neutrino detection for safeguards, for example, the backgrounds from neutrons is a very important background, as well as the muon background. So that is a problem there.
Okay, and there's one question about, it's kind of a vague question, but I thought it was interesting, this application about the muon detection in the pyramid. So can you just say a little bit more about that application and really what all was involved there?
So the idea, this has been done, Louis Alvarez actually did the first measurement on the large pyramid, or actually the second pyramid rather, by looking at muons from the outside. The Japanese team, the Japanese, Italian, French team used actually 3 different detectors. One of their detectors was photographic film. One of their detectors was a proportional counters. And the third detector, I think, was a scintillator. But the idea is that you make a measurement in 2 planes and determine an XY position in those 2 planes. And then from the 2 planes, you can then determine a angle. And you accumulate over time the intensity as a function of angle at the detector. You then have to compare it to a model of the pyramid, because the pyramid is not a uniform solid, and you back project that image. So you start off with a measurement at a plane, and you project that up through the pyramid. And as you move up through the pyramid, you can observe differences in the amount of scattering that occurs at different altitudes based upon that scattering map. And that's how you discover, hidden rooms.
Yeah, that's fascinating. Okay, I think we've touched on most of these, and we're a little bit over time. So I think I'm going to stop it here and thank Dr. Cruz again for your time. Thanks to all the attendees for your attention today and asking such great questions. And we will see you all again tomorrow.
Thank you.
Thanks, Nick.
Thank you.